961 teams submitted viable solution papers in the 2012 Moody's Mega Math Challenge. Of those, 55 were distinguished with finalist or honorable mention prizes, and the top 6 teams were invited to New York to present their papers to a panel of professional mathematician judges.
This whole competition has been fun. Every other math competition that I've ever done has just been you go into a room and you take a test and then you find out how you did. But this is much more open-ended and it has more real-world applications.
You have to really think on your feet when you get the challenge problem and be able to kind of analyze it in a way you've never thought of before. I think for me that was the most interesting part, was figuring out how to approach the problem.
The Acela Express is the only high-speed train in the United States, but prior to its introduction in the year 2000, only 37% of the air-to-rail market in the Northeast Corridor was dedicated to rail.
We used concepts from economics and urban planning in our models this year, so you really need to have a variety of skills where you can really apply the math.
We must determine the program's viability over the next 20 years. These predictions include forecasting ridership numbers for the 10 HSIPR-defined regions, estimating the cost of construction and maintenance, and accounting for the reduction of our foreign oil use. We read the problem, and it was crazy. We had never done this before, and it was just so broad, and we had nowhere to start really. So we just started looking at the internet, looking at the sources they provided for us, and just sort of went from there. It took about 3 hours to start doing some actual work before then, and that was the biggest delay we had. After that point, it was work, work, work.
Some of us, we didn't know each other as well, but when we started working together, we kind of established that dynamic, and you kind of figured out what each person specializes in. So like some are better in economics, some know the physics. So I think once you establish that dynamic, then I think that's most important.
The main point was that we wouldn't actually implement the train project because it really wouldn't save that much energy, and then we calculated that it would take a long time to pay back, so it wouldn't actually be beneficial to anyone.
The first problem we tackled was the ridership over the next 20 years of the various corridors in the United States. The problems that the M3 challenge does is very different because it's real-life applications, whereas when I do a math problem, it'll just ask me like some sort of number, solve this equation, and it doesn't really apply. But here, with the high-speed rail system, it's like my answer really goes somewhere and it's really solving like a real-life issue.
Under 100 miles, it doesn't really make sense to take high-speed rail because obviously it takes a while to get up to speed and then to brake and slow down again. I've had science classes that have helped me write 20-page reports, and I've had history classes that make me more understanding of global issues at large. So it comes from a lot of places, which is part of the reason it helps so much to have a diverse skill set in your team.
I think anytime you're trying to sit in a room with 5 teenagers on a Saturday and do work for 14 hours, you're going to encounter some challenges. So I think the main challenge was trying to stay focused for that amount of time, and it was intense, but I think we did a really good job of it.
Making our population model. We had this first idea, and then we were doing it out, and we realized this isn't really working. So, you know, at that point, you got to go back and you got to say, okay, what are we going to change? And ultimately, we were able to do that, but that was definitely the part where we were, you know, that was definitely the toughest part.
We then utilized this propensity to construct a 99.9% confidence interval.
I think our ranking system was very, it's kind of a novel approach because it was very quantified. There was no subjectivity in it, which I think is definitely important moving to the real world with an issue like this. You need concrete reasons to back everything up.
We want to know, for example, how many of the 6 inner-city commuters in A plan on going to city B?
We tried to have a model for every single aspect of the problem. And so the fact that we broke it down into so many different problems allowed us to cover a lot of ground.
I was focusing on the individual decision-making aspect of the problem. What would make a person decide to take the train rather than ride in a car? And so we looked at both the cost and time benefit.
A lot of the problems we work on at school aren't this long, so to develop a model that's this complex is very interesting.
This corresponds with, say, commuting between a suburb and the main city, because at these small distances, car travel is not only much more convenient, but also much cheaper than high-speed rail.
By the time we got to 8 o'clock, our model was done, but our paper was just a patchwork. We hadn't really combined the parts yet, we hadn't written the summary, the conclusion, and we were missing a sensitivity analysis. So at this point, everyone just like scrammed and went to a different room, and we just like typed as fast as we could, and then combined it
with like a minute to spare.
To find the cost of each train, we looked at Amtrak's past purchase, in which it purchased 20 sets of 8 cars from companies in Quebec and France for $600 million. This average value was used to calculate our total cost for trains.
I thought it was great to actually use the math I've been learning in the classroom, and not as a test, but as a kind of real-life evaluation of how does this math work, and actually thinking about things, thinking about real-life problems.